Last we studied about sound. Now we are going to study about images and their representation using binary. Last time we studied basically sound and its representation in binary. So let's see what is an image, what is a bitmap image, how do we store them, images, sounds in binary, and why do file size vary for different images or audio. Let's link it with prior knowledge, connect with the previous lesson on ASCII, Unicode, and sound sampling. Okay, now the bitmap images are made up of pixels. Each pixel is represented in binary. Okay, and data storage is measured in bits and bytes. As everyone knows, we all have the data that is we measure in megabytes, megabits, gigabits, and kilobytes. So these are the basically measurement of the data. Next, what is the main content is what is a bitmap images? And it is a basically 2D image that is made up of of pixels. Matrix you can call matrix an array of pixels or a list of pixels you can say. Loads of pixels together in x and y axis. So pixel values stored as binary numbers. Each pixel value has basically some binary values. And color depth is equal to number of bits per pixel. Number of bits we use for a single pixel that determines the color depth of our image. How, or you can say a quality of our image. One bit is equal to two colors, two bit equals to four colors, three bit is equal to eight colors, and 8 bits equals to 256, 24 bit equals to 16 million colors. The more number of bits per pixel determines the more number of colors that image can possess, that digital image can possess. Okay. Now let's study about the image resolution, that image quality. You can most of the people call it in our layman language. And now number of pixels in an image, width and height. Basically, what do we have in our computer? We have all the images in two dimensional. So they are width and height. So what we do when we find the whole image, that we find it by width multiplied by height. This is why we measure the number of pixels in an image by width multiplied by height. And higher resolution means more detail means larger file size. Lower resolution means pixelated fuzzy image. Pixelated image is basically you can more of call it in a common language. You can call it a blurred image, image that is not very clear. So next is data storage units. Bit equals to 1 or 0 smallest memory unit, and the byte equals to 8 bits. Similarly, there are multiple other units, kilobytes, megabytes, gigabytes. IHC system uses powers of 2 for these bits. For example, 2 power 10 is for 1 kilobyte, 2 power 20 for 1 megabyte, 2 power 30 for 1 gigabyte, 2 power 40 for 1 terabyte, 2 power 50 for 1 petabyte, and 2 power 60 for 1 exabyte. So all these are in the basically powers of 2. File size calculation. How we calculate the file size? Bitmap image file size equals to resolution multiplied by color depth, number of colors it can process. Mono sound, then for the sound we use sample rate multiplied by bit depth multiplied by duration. Stereo sound means we multiply it by 2. Okay, we'll study that later. And 1024 multiplied by 1080 image and having 32 bit depth, and that will require this much memory, 64 GB memory and 15534 photos. And 2048 multiplied by 2048 pixels, 16-bit depth, that will require 8 MB image. And wait, yes, it has a 16-bit depth. This is why it is a little smaller. And then we have audio CD, and these are basically for audio. There is 605. These are just the examples of the size calculation. Okay. Next is data compression. We have to reduce the file size, and we use data compression for that. There are different methodologies for data compression, and there are two types. One is lossy file compression, other is lossless file compression. In lossy file compression, we remove the unnecessary data and a little quality may be lost. But for example, MP3 audio, MP4 video, JPG images reduces file size significantly. Okay, and then we have lossless image compression. Lossless, we do not lose any data. We just temporarily compress the image, and like original file can be fully reconstructed or can be fully restored. We use the encoding technique that is called run length encoding for that purpose. It encodes repeating data as number plus value. How we will see that in the next slide. Okay, run length encoding reduces repeated sequence in text or image. For example, okay, what does run length encoding do? It reduces the repeated sequences. For example, there is a text compression. This is the textual data and we are compressing it. This data is of 16 bytes. There are 5 A's, 4 B's, 2 C's and 5 D's in it. Okay. Now, in order to reduce this size, what we do, you can say there are total number of bytes it is consuming 16 bytes. How? One byte for A. So five A's will make us basically 5 bytes. Four, four bytes for B. So 5 plus 4 9 plus 2 2 bytes for C, 11 bytes, and plus 5 bytes for D, that is total 16 bytes. Now, in order to reduce this size, how we apply it, we just write the number of times it is repeating itself and we write that count and then we put that element that it is repeated in. First we write the count and then we write that element that is being repeated with this count. So we write 5 A's. Then we have 4 B's, we write 4 first, then we write the B with it. There are 2 C's, then we write first 2 first, then C with it. Then we have 5 D's. What we write 5 first and D with it. Now 5 is also treated as one character. So 5, this 1, 2, 3, 4, 5, 6, 7, 8, count them. It is coming up to 8 bytes. Now with this count, we can regenerate all of this data again. But in some scenarios, the data after compression may get larger. Let me tell you that scenario. For example, if we have the element that is not being repeated like this. Suppose if we apply that, let me do the example 2 of this. Okay, in example 2, suppose if we have the number like this, uh, you can say A, B, A, B, A, B. Now, in order to convert this for how many two, basically two, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now just see, this is a 16 byte data. If we convert it into that, then 1A, 1B, then again 1A. This sequence will be repeated. So this way, after compression, in this run and encoding, the data may become even larger than 16 bytes. So this is why in run and length encoding, we may face this problem. If we don't find the repeated elements, we may face this problem. Okay, so let's move on. Uh, and let's see about the colored black and white and colored images. With this, we see example for the text, and this is the example for the image. Suppose we have a black and white image, and we have 64 bytes of uncompressed 30 bytes with runtime encoding. We can convert 64 bytes of image to 30 bytes by using run length encoding. Let me show you the example for that through the book. I'm going to open the book now. It is contains you can see this in the book. Let me open this book for you, and you can understand the example from the book, and you all need to study it from the book as well, because that will give you much ease. We will also solve an example from the exercise as well. And that will clear our concepts and that will help us a lot in the exam. Just I'm waiting for the file to be open. It's taking a little more time. Okay, let me go back to the first chapter. Okay, you can see this image. This is the image from the slide you can see. This is a black and white image. This is 8 by 8 64 byte image and it has basically what this is F is written by using this black pixels. So how we compress it? What we have, we will in compressing it, we will count all these boxes. First, what we have nine white boxes. Eight. These are eight boxes, and then this is the nine white boxes. What we have written nine and written W with it. Then we have six black boxes consecutively, and another six black. We have written six B. Then we have another one and two white boxes. So what we have written is uh, wait. One, two. Yes, what we have written is two W. Then we have one black. We have written one black. Then we have written these are the six and one seven black, seven white boxes. So we have written as seven W. Next, we have again written one black. So, and again we have written 7W because we have these are next 7 black. Now, there are one, 2, 3, 4, 5. Another 5 black, so we written as 5W. So, this is where you we consider W is equal to 1, B equal to 0, what we get 9160, and so we have converted black and white directly into binary. We have considered 1 for the white and 0 for the black. And this way, when we count these bits, so the total number of these bytes, the total number of bytes become what? They become 30 bytes. So this is how it does its thing. I should add it to my slides as well. Let me let me add this. Okay, I'm going to narrow it down a little. So this will be helpful for everyone. This is how it is And next what we have, next we have the colored image. Now let's see about the colored image. This is the example for the colored image. And in colored image, all the colors are based on red, green, blue, RGB. So these are the colored images you can see. This is the image and shows an object and we have black will be have all the components as 0 and white has all the components as 255 and so what it is taking one byte for each. One byte is 0 to 255 characters. So this is how we are gonna do it. So this produces the following data. How many blacks we have? We have two blacks. For the black, what we write? Three zeros. Two and three zeros. And then we have four greens. And what we did for and for green, what it has 0 to 55 so we return as 0 to 55. Then what another thing we have another three blacks one, two, and three. Three blacks. So for three blacks, what we did three triple zero. And again we have how many? We have six whites. We do six and 255. Repeat the 255 three times. Okay. Let me see. We have four. Let me find it. Yes, six, and we have three times 255. Then we have another one and triple zero for the black because one single black only. Next we have two greens, so we write two and zero 255 0. We get 20250. Next we have red 4 255 double 0, 4 285 double 0. Again four greens, 4 0 to 55 0. Again, we have 4 0 to 55 0. So this way we count it like this. Now, the original image 8 by 8 would need 3 bytes per square. Okay, so all of these red, green, blue, red. So one byte for red, one byte for green, one byte for blue. So a single color will take how many bytes? 3 bytes. So and one byte will be consumed for this count. 1 plus 3. So they are basically in 4 bytes we have converted uh, those that 12 bytes is converted into basically 3 plus 1, 4 bytes. So this way, what happens? The original image size is what is 8 in the horizontal and 8 in the vertical is 64, and each color takes basically 3 bytes. So the original size of the image is 192. But after applying this RLE encoding, what we have found that our size has become 92. How? Let's count it. Uh, so these are basically what representing 4 bytes. 4, then again 4 plus 4 8, 8 plus 4 12, 12 plus 4 16 plus 4 20. So 20 are done here. So 20 plus 4 28, 28 plus 4 32, 32 plus 4 36 plus 4 40 plus 4 44 plus 4 48 plus 4 52 plus 4 56 plus 4 60, and then again 64 68, then 72, again we have 72 plus 4 76 plus 4 80, 80 plus 4 88 plus 4 90 and 92. So in total it becomes 92. I think I have a little slowness in the calculation. That is why it may have confused, but it is actually. So how much file size is reduced? File size is reduced by 52%. So this is it for the today's class. Let me copy this example as well here. So we have to write this as well, and we copy paste this. Let me rewrite it in this format. Okay, let me write it the black color as black. So next is 0 to 55 0. This should be what? Green. Let me make it green for you, and green should be a little better. Let me make it this green. Then after that we have another black, 3 blacks, and we have another white. So for white, what we should do, we have 6 W's. We can call them as, I'm going to let me set the white color as something very close to white. Okay, let me call it basically what. For the white color, I should use a little different. I'm going to use the gray color for the white. And next what we have another black, and after this black we have another 2 greens. Okay, for 2 greens what we have done this. Then 2 greens we have how many? 4 reds. 25500 is for the red, and let me make it red for you. And what we have, another two greens and another four greens, then another green, then after those four greens we have one white. We will do it that way, we will make it white. And then we have, after single white, we have another two reds. Let me make it red for you. And then we have, after two reds, we have another white. For white, I've already told you that for white I'm using gray. And next what we have for 40 to 55, and that is for the greens. We have another four greens, so I'm going to make it green like this. What we have, another four reds. Yes, we have another four reds. We are going to go with this. Next what we have, we have another four greens. So what we will be doing, we will be making, we will be setting red, green here. What next we have another four whites. So what we do for the white, we are using gray, and we have another two greens. For the green, we will be using like this. Then after the greens, we have what? One, one black. Okay, let's keep it the black. And next we have two whites. For the whites, let's do it that way. Oh, sorry, I'm using gray for the white. Sorry, I forgot that. And next, what we have another two reds. Let me make it red for you. And this is the red one. And next, we have two 55, another two whites. So for white, we are using gray here just to represent that. And let me do it for another three zeros. This is black, and another, these are greens. What we are doing is this is as green. And now, okay, now I should style its background. Let me fill its background with not just black, we use it with, you can say, I can call its background as yellow, or I should fill it with a little better. Let me find some better color for you. I think this one is even, let's do it that way. Okay, let me. So this is how we are representing this one. Now I'm going to make the white as white. So this is why I just converted it into that, because that will ease up the things for us. I think all the students will understand all the things that I've explained so far. And this is how we are gonna end this suffering. That's it. So this is how we are representing this image, and this is basically giving us 92 bytes, and that one, the other one was giving us 192 bytes. That's all for this class. Thank you.